Okay, so I believe we are ready to start. Just let me put the shot over here so I can see. I have here the key and the okay, let me see if everything it's okay. Okay, so I'll start. I hope everyone is listening. Today's tutorial that I am giving you today is about biomedical text processing using semantics. The idea is to have a hands-on tutorial with shell scripting, where we mix these introduction steps for processing text and also using semantics. My name is Francisco Couto. I come from the University of Lisbon, and I hope everyone is hearing okay. So I will go for the first slide. So the question is about why should we work with biomedical text processing? Why? So what is the importance of having biomedical text processing? So as all you already know, every drug that you buy on your drugstore has information leaflets that has all the indications, all the problems about a drug that you can have. And this is text. This is not data. This is text. Why? Because text in the biomedical sense has to cover all the known contexts about a specific drug. So this is something that a biomedical text that everyone already read, because everyone took a drug to treat some kind of disease. And this is the reason why we have this biomedical texts to cover all the aspects of our entities. And this is especially important in the biomedical field, is that we have always a context bias. Okay, so we can always see the same thing from different perspectives, and text brings this perspective to us. So this is just an introduction to the team, and just an optical illusion. As you can see, all this bar here is of the same color, but since we have a different background, it seems that the bar is different, but it's the same. So depending on the context that we have, some facts can be interpreted in different ways. And even the context changes the impact. Sometimes when we know something and we know the context, we know that what is described in literature, then we know that the impact is greater than we thought, or lesser than we thought. So this is also an optical illusion, where the circle has the same size, but with around the context that's around the circle, we can see that here this circle seems to be much smaller than this one, and they are exactly the same. So the text is very important in biomedical, and also we have the time feature. Okay, our knowledge about the biomedical information that we have changes along the time, and this is just one example. This is from Reuters, one article from 2018, and the other article from 2020. And as you can see, that's here you have that 1 egg a day is good for your heart to lower the risk of heart disease. So it's a good thing to eat eggs. And then after 2 years in 2020, eating eggs may not impact our health at all. So the content changes, it's dynamic, and we have to process all these texts to know what we are looking for. This is another example to know the importance of the context that is written on the biomedical text. So nowadays with the pandemics, everyone knows about these graphs. And this is a graph, this is a Google Trends graph from 2017 ends with 2018 here. And this is the number of search terms, the number of search for tuberculosis cure. So in the United States, but worldwide was the same. And as you can see in 2017, there was no much search for tuberculosis. But here in the middle of 2018, there was a peak about search for tuberculosis cure. So if we look at this data without the proper context, without the literature, we can think, okay, there is a pandemic here, and in 18 and 2018, there was a pandemic about tuberculosis because people were looking for tuberculosis cure. As you know, it's not true. Why? There was an expected context, okay? So there was a game that was released that was Red Redemption 2, and the major plot was a guy that had a bacterial infection that caused tuberculosis, and then people started to look for cure for tuberculosis, but about the game and not about the real life. So this is an expected context that sometimes happens. And this is another example why the context, why the text, why we have to process the text. So this first part is just to motivate you to process biomedical text. And this is another thing that, for instance, peanuts can be beneficial to your health, but it can also have life-threatening reactions. It depends on the context, okay? It depends on the patient. Sometimes if you have allergy, something that seems to be beneficial can kill you. Okay. So where is the context all about these biomedical things? The context is in scientific text, okay? You can go to PubMed, for instance, and you can search for every article that is published in every area of life sciences. And it's all there, and you can look for it. So text is still the professional means to publish new discoveries and the context that support them, okay? So everything has to be grounded with evidence in a context, and this is on text. And why text? Because humans need that flexibility to express their hypotheses, their ideas, their opinions, because sometimes some findings are not facts that are general to every context, but depends on the context, and that has to be explained in text. So computers, of course, doesn't like so much text, so they prefer structured data, so we have to deal with this problem. The other problem of biomedical text is the large amount that we have available to process. So this is just an example. Here you can see that almost 1 million scientific articles were indexed in 2019 by Medline. And just to figure out the scale about this, if you read 10 articles per day, you will take more than 262 years to read the articles that were published in that year. So it's an amazing effort if you want to read that manually. And this is just scientific articles. We have also, this is the growth of citations in Medline. So this is the scientific papers. But then you have clinical trials. They are text also, and you can see the growth here, the exponential growth here. You can see the patents also that describes new findings. So as you can see, all this text is not disappearing, it's growing, and we have to process it. Of course, you can make the question, okay, why we don't do something like in Wikipedia and we try to gather some human annotations for all that text and everything goes to databases. The problem that we are dealing with a very complex domain. Everyone knows about nowadays about pandemics and see how it's complex to build information about that. So, and selecting the right terms, it takes time, it requires knowledge, and it's very error prone. So people choose different terms depending on their background. And when we work with these approaches, we have a lot of problems with missing values. The doctors don't put the values there because they don't know, because other reasons. And sometimes they also pick generic terms. They are too generic to be useful. Okay, so be free to ask any question in the chat. Okay, if you have any doubts. This is just the first part where I try to motivate you for the rest. So about what is the solution to this problem of having to process all these texts is text mining, of course, and is in a way to transform the free text to a normalized and structured data. So in the sense, trying to enable the algorithms that we apply to the data, to structured data, like machine learning and so on and so forth. So, okay, so this is about why text, biomedical text. So the next question is, why semantics? Why do we need to process semantics in this field? Okay, so here, the main problem that we have in the biomedical field is the complexity of the message, okay? Everyone can, if we are dealing with newspapers, with tweets, or something like more generic, everyone can understand what is in there, okay? Almost everyone can look at the text and see, okay, this is about this and describes this. But if you read a scientific article, then it's very hard to understand it for the general population. And also, like I said, has different interpretations. So in biology, as we all know, all the cures and treatments has exceptions, everything has an exception, and everything has to be documented and reported. And then you have another problem that is the multilingual aspect. Okay, nowadays with the clinical trials, with the electronic health records, we don't store everything, every information, every knowledge in English. Okay, if you go to an hospital, normally it's not a problem in the United States, but in Europe, every country has its own native language, and the clinical records are normally written in that record. So if we want to process at a larger scale, we have to deal with this multilingual aspect. And the main problem why I'm speaking here is the problem of nomenclature. Why it's not consistency. In the scientific articles in the community, they use a given acronym. In another community, they use another acronym. They are not consistent a long time. They change the names. So that's a problem for someone that is trying to process text. So this is just another example. For instance, if I say cell, what do you mean by cell? What is your interpretation by cell? It depends on your group. As you can see by the figures, it can be a cell from biology, cell from Excel, a cell or phone, a cell from prison, electrical cell. So it depends on the context that I'm speaking about cell. There is I don't know if you are aware, but there is a interesting sentence about this from Dumpty, that when I use a word, it means just what I choose it to mean, neither more nor less. So when I use some expression, it normally depends on the context of the author, and we need to know about that context. So where we get this context and this domain, we have the luck. Fortunately, there are a very high number of initiatives that are working on building vocabularies and ontologies that list all the entities and concepts for a given domain. They give the official names, the synonyms. They are always updating this information. And they also provide semantic models because there are ontologies that provide relationships between those concepts. So this is where we can get the context to understand what is in there. And since this is ontologies, this is structured data, computers can use it to get the knowledge they need. So this is one of the first examples of ontologies in the biomedical domain. So this was a list of the possible way to die that was in the 16th century. So this is a vocabulary that people use instead of every doctor's expelling the way of dying wherever he wants. He had to pick from this list. There were no computers at that time, of course, but already make possible some statistics about London in this case, about the deaths in London. Okay, nowadays we have, this is a case from the gene ontology, an example. So you can see that now we have, these are the terms, the relations between the terms, and then we have proteins annotated with the terms. This is biological process. So we have all the proteins from different organisms here that we know that belong to this biological process or participate in this biological process. So these graphs here is what we can use to process, to use semantics to process things. Okay, so the last question before going to the hands-on tutorial is why shell scripting? Why I'm here on a tutorial to learn something that is done in shell scripting. Shell scripting is available for more than 4 decades, so it's old stuff, but it's now available in almost all the personal computers. So even Windows tried to get PowerShell, but nowadays with Windows 10 you can install Linux subsystem and it's everywhere. And it's something that everyone uses in the for instance, in the bioinformatics field, to solve some daily challenges, daily problems that we have to mix data and so on. And as you can see, it's not getting away. It's becoming more available. So the reason why we use shell scripting for mostly for solving the problems that we face daily is that this is an article from Forbes magazine when they say that 80% of the work of data scientists is about data preparation. Okay, so we all like about working in mining data for patterns, but this is 10%. We apply the transformers, deep learning algorithms, but this is most of the time 10% of the time. Where we spend the time is collecting the data, cleaning the data, connecting the data, and this takes a lot of time from people. And this is where the command shell, the shell scripting and Unix commands work better, because we are collecting from one place to another and so on, and they are very flexible to do this. This is an example and a use case from a company that is Unicage, where they, for instance, take 50% less time in some process by collecting, cleaning data sets using shell script instead of all the fancy tools that can do this. So it depends on the task that you are dealing with, and for a starting point to know how to process text and semantics, what I advocate here is a very strong tool to start. Okay, and to understand the things. And not always, this is just a joke, not always all tools are sometimes the best solution, okay? It's always, like I said, this is from 1980, and people used masks also. And nowadays we are using masks. So like shell scripting, 4 decades ago, we used shell scripting. So there is no problem in using shell scripting nowadays. Sometimes all tools are really the best solution, depends on the problem. Okay, this is an example that if we have all the time and finish, we will work with this tool that is a tool to perform name entity recognition, and it's full. It's all about shell script with Unix commands, and it was built for being minimal and very flexible. So I will not explain this in detail, but it's about grabs and divides the lexical, the vocabulary in different files, so it can be quicker. And as you can see, it was evaluated in an international competition, and it reached very good results, even with being a very small and a shell script based tool. Okay, and you can try also on the web. Okay, and so we will now go for hands-on tutorial that is based on the book that is on the website. Before starting this hands-on tutorial, I would like to ask you to go to the website of the workshop, and there is tutorial slides link. It's the biggest one, so you cannot miss it. Please download it, because I will follow now those slides, and also enter the comments in the shell, and we will go together trying to process text and semantics. Okay, if you have any question, please let me know. I'm trying to see, there is no question here. So by the way, this tutorial is being recorded, but we can edit the key and way afterwards. So if you have a question, feel comfortable to ask. We will edit and we will remove it from the video. Okay, so don't worry about making questions. So I will assume that everyone already got the link and went to the web page. So I'll do the same. So now I'll just stop sharing. And go and see the tutorial slides. Okay, so let me share again. So I hope everyone is now seeing the slides, and then everyone has these slides. Okay, if there is a problem, please let me know. Okay, I will go through this PDF now. Okay, so some introduction now more in detail to semantics. Like I said, the problem is that we have lack of standard nomenclature, so everyone is using its acronym, and sometimes we have problems with synonyms, acronyms, homonyms. So there is we require sense disambiguation about it. So some acronyms can mean different diseases. Okay, so the idea is to use ontologies. Like I said, what is an ontology? So there is a definition here that is from 1993 that is an explicit specification of a conceptualization. So specification is a representation of something, and conceptualization is the concepts that we have in our domain. So it's explicit representation, so we can work in the computer. So then it was refined to be also formal, so the computer can deal with it, and also shared, so it's not the conceptualization of the individual, but from the group of that domain. Okay. So like I said, the conceptualization is the abstract use of concepts with relationships. These are already said, and the specification is a representation that needs to be in a given language, so computers can deal with it. So which kind of language do we have to represent ontologies in the biomedical domain? We have the traditional one, that is OWL, the web ontology language, but we have also the open biomedical ontology, OWL. So many biomedical ontologies also use this language, but most of the times we can get both versions, and here we will work with the OWL version. Okay, so concepts in these ontologies, I will not give a tutorial or a lesson about ontology, so I will just give only the concepts that you need to know to work with ontologies. So you just need to know that these ontologies are like dictionaries that have described concepts. These concepts have multiple properties, like the labels. Labels is the synonyms they have, so how they are mentioned in text, names, acronyms, and so on and so forth. And we have different levels of formality, from just a list of control of concepts and the names to taxonomies, and that work with the structure, the relations between the concepts. So we have normally this ECIR or subclass relations, that we have a class that is a specific case from the other class. So disease is a specific case of another disease, like COVID is a specific case of an infection disease. Okay, so it's trying with a very simple example. So you can consider this as an ontology, and see that these ontologies are DEG, so they are graphs, they are directed and cyclic. We don't have cycles here, cycles, and we have multiple inheritance. So we have gold and silver being coinage, and coinage being a metal. Okay, this represents this subclass is a relationship. Okay, from the most generic term to more specific terms. So what is the about the retrieval? For instance, we are in a conference of information retrieval. What is what can we do with this ontologies? So imagine that we want to find text related to gold, and the corpus that we have I can go to this figure here. So we have a corpus that mentions platinum, palladium, silver, and copper, but there is no document describing gold. Which one should we present to the user first if he search for gold? We can use this ontology, because we can see which term is closer in terms of semantics, closer in terms of this domain to gold. Okay, and in this case, probably it's silver, because it shares both the notions of being precious and also metals of coinage. Okay, so this is what I said. Where can I find these ontologies? You can go to BioPortal, and this is a number from 2018, probably already the book has more larger numbers than this. So, but it's about almost 1,000 ontologies, probably, and it had 9 million classes, so 9 million concepts described there. So if you go to BioPortal and search for caffeine, you will see a large number of ontologies that describe it. Why? Because they have different interpretations, different contexts from the same concept. So caffeine can be seen as a chemical compound, or an ingredient to food. So depending on the context, these concepts have different interpretations. So, and there is also a very important initiative that is the OBO, Open Biomedical Ontologies, that tackle this somehow disorderly way that ontologies are being generated, and they have an organization for that. So they have principles where people have to follow and divided by different domains. Okay, so one of the most successful ontologies in OBO was gene ontology, that describes molecular function, biological process, or component for describing gene products like proteins. But today we will work with the disease ontology, that it's much easier to understand. It's about human diseases. Okay, it's an ontology about human diseases and phenotype characteristics. And another one that we will work also, it's about chemical entities. Okay, that have some biological interest, but they have all these chemical compounds represented on that ontology. There are others. If you are interested in checking other domains like the International Classification of Diseases (ICD), the SNOMED CT, that is very comprehensive, very large. You have MESH, that is a medical subject headings that are annotated. All the abstracts in PubMed have this medical subject headings annotated to classify this text. And of course, you have UMLS, the Unified Language System. It's a very large resource that integrates almost every ontology in the field. And so you have different approaches to it. One good thing about OBO, everything it's open. So here in disease ontologies and KEVI, it's open. As you will see, we can go there, download, work it, no problem with it. Okay. Another place where you can see these OBO ontologies are in Ontology. That is also a portal for getting these ontologies. Of course, if you want to go outside the biological domain, you can go to other places to check these vocabularies. Okay. So how can we start using ontologies? The first thing is to download ontology. It is what we are going to do in a few minutes. And for instance, then we have to select the version that we want. Sometimes ontology have different versions. For instance, KEVI has little, core, and full. Here we will only use little, light, but there are other versions that accomplish more properties about the concepts. Okay. Okay, not going too much in detail in OWL. This is not a lesson or truly about OWL or ontologies. You just need to know that OWL is a language that extends RDF schema, and and RDF schema is an extension of RDF. Okay. And this RDF is a data model that we can have this link, these concepts and the links between them. It's what we need to know. So it's a data model that is represented by this triple subject, predicate, and object, what we will use. And we will use this data model can be encoded in different ways. We will use the XML, that is the most used nowadays to store the ontologies. But there are others ways to encode this RDF data model. Okay, so we will have to work in the command line with XML. Okay, we will use XML files and try to process that represent those ontologies. So this is just an example. So what this XML looks like, it's like you have these elements, and these elements have properties, and the properties have values assigned to it. Then you have other entities here, other elements that can be inside the other elements. So this drug here is inside the treatment, the condition is inside the treatment, and then the treatment clauses, and you can see that this caffeine is a treatment to sleepiness, is what we are trying to say here. But this is just an overview of what kind of things we have. Okay, like I said, there are other languages to encode RDF, like N3 and Turtle, but we will use XML encode. Okay, I believe that everyone knows about this. So these ontologies that we are using have as primary key as the identifier, the universal identifier. They use the uniform resource identifier, the URI, and so here this URI is the identifier of caffeine in the ontology. So if we want to mention this term or link to this term, we should always use this URI. Okay. So what we will do to work with these XML files is using SysPath. Okay. SysPath is an XML path language that is like a query. Okay, it's like we use in SQL to look for data in a database. We use these SysPath queries to look for data inside a file, an XML file. And we will see, I will not go in much detail, but I will show you the examples that you need to know to process the ontologies. Okay, so some examples. So if you have a query, if you have a file, XML file, and in this example is about the protein. Okay, so if I go to this website, if you go to this website and see the XML file, you see that there is a lot of information there describing the protein. And if you make a query, SysPath query of that file, if you look for DB reference, these 2 backslashes means that it can be in anywhere on the document. It will get you all the elements named DB reference. So you can see that this is the element DB reference and another element DB reference. All the elements in the file, wherever they are, they will show on your screen or to your file. And then you can also use this hierarchy. Okay, you can say that, okay, I want a DB reference that is inside an entry, an element that is named entry. So this will show you the same DB reference, but we are specifying that we need to know that they are inside entry. And then we also can give the full path. Okay, I can say I want the DB reference element that is under citation, that is under reference, that is under entry. Okay. If we want the children of the element, then we can use the star here, and you can see that this property is here. This element property is beneath, so it's under the DB reference element. Then we can also get just the first one, just the first element property that is under DB reference. The first one, the second one, or the third one. Okay, it's just standard ways to get this information. And then we will also have the permission to get some properties of that element. So as you can see, these properties here, this is the element name property that has properties inside bin. And we can check which kind of values these properties have. And for doing that, we use the add character, and we can see that the add character type, so we will get all the attributes of property that are named type, as you can see here. Okay, or we can also get the previous property elements, but where the value is protein sequence ID. So you can see that if I want the ID of proteins sequences, then I can use this SysPath query to that file, and I will get all the IDs, the protein sequence IDs of that protein. Okay. Then we can also have these conditions and then get just the value of a given property. So this is just adding a new query here, a new part to the query. And then if we need also what is inside an element, the contents, we just write text. And for instance, the element sequence containing the sequence, this is the sequence of that project that is shown to us. Okay. Any question? We will see in practice this working. Okay. So let's start our hands-on. So all of you need, if you want to follow what I'm doing in your laptop, you need something like this. You need a terminal, okay, where you can write Unix command lines. So I hope everyone has one available, and we will use a very small number of command line tools. So we will use curl, that is to download data. We give a URL and it gets the data for us. We will use grep, that is a way to search a file for a given lines that match a query. We will use also AWOC. In our case, this is a very powerful tool, but it's just to find the right columns in the text. We can also use sed to replace some strings, and chizards is a way to, if we have a list of things, to apply a command line to all the lines that are in that file. Okay, but more important here is that we will use XML links that we can add shishpath and a file, and you do provide the answer to those shishpath queries. So we will solve the examples that I described before. And then just the normal command lines like cat to see what is in the file, the tr just to replace one character, sort to sort one file, the lines, and sometimes have just to see parts of the file. Okay. So the first thing, it was on the web page that you needed to see if you have everything installed on your computer. So if you have all these comments that I described before, installed on your computer. So I hope you did this, but I will do it just for you to see how it is easy to test if everything is working. I will now just let me, because I have to change, because I now want to show also the shell. I will just stop it for a moment. Just let me. So if you have any questions, please let me know. Okay. Just let me check this out. Just a moment. Now I want to share the whole screen. Okay. This here. Just let me try to share now the screen. So I'll not share everything. Okay. Please let me know if you don't see the screen. So I'm showing you now the PDF file with the slides and all my files also, and I will open a terminal. And I have nothing here, so I'll try the comments so we can see. So the first one is just getting the script. Okay, so I will get the script, and for doing that, I will use the curl command that has this option, the O option. So it saves as a file in my computer named by the name of the last part of the link. Okay, so I will just copy this. So I hope everyone has the PDF file, so you can do also the same in there. So you have to copy each line each time, otherwise we'll also copy this thing that's saying that the rest of the command line is in the other line. So I'll just download the file. The file is already in my computer, as you can see. Now I will just unzip it. Okay, so the file is in there. I will change the mode in some, I believe in Windows, if you are using Windows, you don't need to do this. But I'm just saying to the operating system that this file can be executed. That's all. So change mode, the user can execute this file. Nothing's fancy, okay? Then I run.
Excuse me, Francisco. I think we have a problem with the visualization of your screen. I send you a screenshot in the private chat to show you what we have.
Okay. We just see a screen. Just let me stop the share and try again. Can you see now?
Yes, perfect. Thank you.
Okay, sorry. Okay, so what I did here was just download the file, then unzip the file, then changing the permissions for that file so it can be executed. And then I will just execute the file. Okay, it's just normal. And as expected here, all the comments are low and the text is okay. So if you have any problem with this, please wait for the coffee break and try to see some of these videos where I explain also how can you install the things that are missing. Okay. So let's go to fetch our ontologies. So as you can see here, these ontologies are available using these URLs, and where I can find these URLs, you can go to BioPortal or Ovo Foundry. They are described there, and I'm just using curl. Okay, you can use, of course, the browser, but I'm just using curl. And the only difference here from the previous command is I use the L option that follows redirects, because this is a link that redirects to another link, and I want to say to curl to follow that redirect. That's it. So I'll just get the file. So it can take a while because these are large files, okay? Don't forget that I have to copy one line and then the other. This is just easy. So then I download the other. Okay, then I just unzip the file because the cab is really large, okay? And as you can see, now we have both ontologies here, and you can see they are very large. So Cavi has more than 100 and almost 160 megas, and the disease ontology is 27. Okay. So we now have the ontology of diseases and of chemical compounds with all the human diseases and all the chemical compounds described on the ontology. And we can see, try to see what is in there. You can open, of course. Let me try just open. You can just open and see what is in there, and you can see that everything is here, but it's XML file. It's an XML file. It's very hard to understand. But we can apply some graphs just to see what is in there. If it has what we are looking for, just let me search for instance, for a disease, malignant hyperthermia. That's something that I used previously in the book. And you can see that the disease is in there. Okay, so there is a label. You can see a label that describes malignant hyperthermia as a label of a concept. Let me check for caffeine, if the KV has caffeine, and also the file has caffeine in there. Okay, so you can see that we have two elements, at least, that describe these two concepts. Okay, so this is just to see if it is in there or not, but the way to query the XML file is not to use grep, of course. Grep is just to filter lines, and the XML file is a structured text that is structured by elements and not by lines. So we need to start using our XML Links tool. And for doing that, I will just copy and paste and explain what we are doing here. So don't forget the space. Here, there is a space here. So what I'm doing here is, okay, I'm using XML Links. And I say, okay, I want to use a shishpath that query that wants to find the element label. So see that label, it's the thing that I want to find. And you can ask, okay, but there is something strange there, local name equal. This is a little not so pretty way to use XML link, but this is a very small tool. So since this is using a namespace, I will not describe in detail what is a namespace, but it's somehow giving a name, a URI to a given domain, in this case, the ontology. We have to say that we are using the local name, okay? We want to search for label that is a local name on ontology. So the name that we have after RDFS, okay? So we want to search for the element label, that is a local name, and also that which the text, so the context of that element, this is the element, and this is, as you can see, the content that is inside the element, because the element ends afterwards. And I want to get the element that contains label as an element, and then the content is equal to malignant hyperthermia. And then I just go, like in the directories, I go up in the hierarchy, so I will find the concept that has this element label. Okay, so let me run. So what we have here is the class. See, you have the class that has our URI that defines the primary key, the identifier for this disease, and then all the information that is in the class. You can see here where is the label. Somewhere here is the label. We see here is the last one. So you can see that what we were looking for was for this label, okay? And then we went up one step in the hierarchy, and what we get was the element that was the parent of this element here, okay? So we obtain all the class about this disease, okay? So we can do the same for caffeine. So this is the result that we should go. I will first put the caffeine so you can see. So if we do for caffeine, this is the same thing, but this is here you just have to use the caveat lights out, and here you must use cafe. Okay. It takes a little longer because the file it's much bigger. So you can see all of this is about the caffeine. Okay, all the subclasses, all the information, but you can see here again that the level of this class is the caffeine. Okay. Of course, you can use now this link. Just let me now do the same, but just get the first line. So I will just use an add. And you can see just to check, okay, this is a link for the class. So if we click on this link, so just let me open the link. So you can see here that this is malignant hyperthermia, like we were expecting, and all this information that is in here is also described in here. Okay, so this is just a visualization of what is in here. If we do the same for caffeine, so I just have and also apply, try to open. So copy link and put it here. So you can see that we get everything about caffeine. Okay, so all the information that we have here in XML file is also in here on the browser. Okay. Okay, so any question? No. Okay, there is a question here. Just there is a question on can large scale open cover. I don't have the open here now, but if you have questions, let me see if I can see the same question. I'm just trying to find the question in Uber because okay, there is a shot here. Okay, just let me put here. So you were not using the shot of Zoom, but of Uber. Sorry about that. I was not seeing your questions because I just looking to the shot. Okay. Okay, so probably everything is now working. Sorry, I was not looking at the shot in Uber. Okay, I was looking at the shot in the Zoom. So there is a question: can large-scale open collaborative knowledge graphs produce Wikidata and DBPDB be efficient in biomedical information retrieval? It depends. Okay, we have some experiments with DBP, for instance, to perform entity linking. The problem is that they are very generic terms. Okay, these ontologies here that you are seeing here, I'm using caffeine and I'm using malignant hyperthermia, but they have very specific terms. Okay, they are very specific to that given domain. And if we are doing this entity link problems, text mining problems that are specific to a domain, using these generic ontologies sometimes don't give you the right knowledge that you want. But we also use sometimes, for instance, in question and answering, we use sometimes these generic ontologies. Okay, I hope I answered the question. Okay, so I will follow now. Okay, so as you can see, there is some subclasses here. What we know is that, for instance, in this case of caffeine that we are seeing here in the bottom, we see that caffeine is a subclass of these two chemical compounds. So if we go into this URL, we will find the parents of caffeine, so the more generic terms. The same happens for malignant hyperthermia. And that we can see. Let me bring again the page about You can see about malignant hyperthermia, that is much easier to see. You can see that malignant hyperthermia is a specific case of autosomal dominant disease and autosomal genetic disease, so on and so forth, until we also is considered a disease. So it's the most generic term. And these subclasses are described here. So if you, for instance, copy this link and go in here, you can see that you get the autosomal dominant disease that is apparent. It's not now here, but is a parent of a malignant hyperthermia. Okay. So going forward, if you have any questions about what does it mean being a subclass? Okay, this is about caffeine. That is the same thing. Okay, so another thing that we have also is related classes. So sometimes we don't just want the parents, the more generic terms, but also other classes that are related to that concept. For instance, the related classes of malignant hyperthermia, if you see in the site the same thing, you can see that there is some related classes that you have here as material basis in some autosomal dominant inheritance. This means that this is not a special case of this concept, but has also a relation that has material basis in. Okay. This is more clear in the carry, where you have a lot of relations like as role in another chemical compound. So, for instance, caffeine has a role in mutagen, for instance. So you can see that the graph that we have about the concept is not only about the ECIR relationships, the subclass, but also other types of relationships. So let's see that relationship for the caffeine, that has this relation has role with mutagen, and where we can find this in the XML file. So we can search here, just let me copy, for the object property. Just let me copy here. Not copying correctly, sorry. December 2. And then file. Okay, so what we are doing here is just trying to find these objects properties that tells you about some property which local name is about this URL. So the local name about, like I said before, is we are trying to find the element about, and the element about describes the primary key, okay, the identifier of that class. As you can see, this happens for all the classes that we have here. So you have, it starts always with class and then RDF about, and then you have the primary key. Okay, this is triplets using RDF. So we will get, what we will get in here is these objects, as you can see, that have here the identifier of that relation, and you can see a lot of information. Let me just open this a little more so you can see this clear. Okay. So you can see that this object property here is about the relation. This relation is this number here, the 87, and is about a relation that is not, in this case, it's not cyclic, so it's false. It's not transitive, it's false also. And as you can see, it's about the relation that we were looking for that has role in there, okay? So this is information about that specific relation that we have here. Okay, that was here in the cavi. As you can see here, probably this is about cavi. You have here subclass, and then I'm not having it now, but it's somewhere here. Okay, I'll not it's here. Okay, so you can see that all these relationships here are relationships using this relation. Okay, so this relation 87, that is as well, and you can see that these are the compounds that of which caffeine has a role with. Okay, so I will just found that information about the relationship. Okay, so it's not transitive, it's not cyclic. I cannot have cycles with this. This is an image of the same information that we have here in the English. Okay, so one of the first, let me see if I have any question. No, I believe everyone is following. So we until now we just went there and trying to figure out what kind of information we have in the files. The first thing we will try to do is work with URIs and labels. Okay, for text mining, to process biomedical text, we need labels. Okay, we need the labels of all these concepts, trying to find out where they are in the text. But to work with an ontology, we need these primary keys, these keys that are the URIs, the identifiers of each concept. So a way to use this is always to have a way to find the labels for a given URI and vice versa. So to get a URI for a disease, what we can do is do this command line here. I will just paste it and then explain. Don't forget the space. Then put it here. Okay. What just happened here was I just applied this path where I was trying to look for a label. We already done. It's the same thing, and also with the text equal to malignant hyperthermia. Okay, so we found in the sense the class until here is the same thing we did before. So we found the class that describes malignant hyperthermia, but then we want to find the property about property because we use an at here. So this set is to get the property about, and the property about is where we have the identifier, the URI of the class that describes malignant hyperthermia. Okay, so as you remember, let me just, because probably you already. So this is the same thing. It will show the class. The only different thing that we have was this part here, okay, where we, inside this class, we wanted to find a property, and you see the properties are inside the element, the beginning of the element, the property about, okay, and the property about is what it describes the URI. Okay. Any questions? So, of course, you can ask, okay, here we have not just the URI, but the all property syntax. We just need the URI. So one way to do it is to add string to the shishpath carry. So I just use the same as before. I go here. I just add string here, and then I just get the URI. This works very well if you only have one match. Okay, if you only have one match, if you know that this will always get just one class, then it works. Otherwise, if you want to get multiple URIs that we want, because you will see that we have ambiguity, then we need to use other techniques. Okay. So we can do the same for Kev. So let's get the same information for Kev. So I'm using two ontologies, so you can see that every ontology from mobile is the same syntax, and the others are also very similar. So it works the same way in almost every ontology. So I just go here. Okay, I just get the same information, but now about K-theme. Okay, I get the URI about K-theme. Okay. Okay, everyone comfortable? Yes. So we are now trying to do the first script. So this will be just a few command lines, don't worry. But we will just join these comments in a script that can be used to get the URI. So I just give you, the idea is, okay, I give you a label and you get me the URI. So I will do this just by the command line, but if you are using other system, you can use wherever text editor you want, Notepad if you are in Windows, or VI if you like the shell editor. I will use Emacs, but it's the same thing. Okay, so I will just create. So this is a text editor. Okay, if you don't have Emacs on your shell, if you don't want to use Emacs, just open your Notepad and write the file in the same path that you have the shell. Okay, so I will just open the file get URI.sh. Okay, it's new, there is nothing there. So I will just copy here. So this is the number of the line, so don't copy the number of the line. I'll just paste here. So this is for anyone that doesn't know anything about shell scripting, this is very simple. I'm just creating a variable with the argument that I take from the command line. So the first argument to the command, to this script, will be the OWL file, the ontology. Okay, I get the name of the ontology, and I'm just using the file name stored as a variable OWL file. Okay, nothing fancy here. This is the same command that we did before. Okay, I have to clean this up. Okay, so what is different here is that, so you can see that it ends here. What we are doing now, I'm using the file that I received as argument, applying the XML links to it, and then also looking for the syspath with label. And here we have a different thing. Okay, I have these brackets here. What does it mean? This means that I'm applying the command cheeseargs. The command cheeseargs is a command that applies the same command, so the same command that is inside cheeseargs, that is XML links, to every line that I receive from the standard input. Okay, if I give him a file with a lot of names, you will get the URI for all those names. Okay, so then I just say, okay, the rest of the command goes to the next line. So after getting all this information, since I have some kind of ambiguity, what I will do is, instead of using string, I will just replace the commas by a new line. So every time I found a quote, sorry, a double quote, I just change for a new line. So the URIs will get in every line alone. And then I just grab for HTTP. So I get rid of all the rest. I just get the lines where the link is there. Okay. And that's it. If there is no other question, I just save it. Okay. So you save it on your text editor, and you can see, let me show you here are my files. As you can see now, the URI is here. Okay, this is a normal file. I just created the file here. You can open with another. I just have this one. Let me see. Text edit. Okay. Okay, it's a normal file that you can edit also from here. Okay. I'll just close. Just go for the terminal. Okay, so don't forget to change mode. So we need to say that this file can be executed, get URI, and then I just get, sorry, just going without moving the slide. So I just change the mode of the get URI, and then I can now use this script to get all the URIs for a given name of the disease. So what I'm doing is giving as a standard input. In this case, I'm just giving one line, so one name, and I apply get URI with an argument being the ontology. So, and you can see that now I can use this script to every disease that you can try. So, and we can do the same for caffeine. So caffeine, we apply, and now we have a script that you can search for every disease or chemical compound, and you will get the URI as output. Okay, no questions. Let me see. Okay. So now, like I said, the reason why I had Xml is to have multiple strings, multiple lines as to look for the URIs. So let's try now with two diseases. And just to see what is in here, this echo here, I just added the new line between them. So the result is a two-line output where each line contains a disease I want to look for. So if I apply this now to get URI in the disease ontology, oh, sorry, just forget to add it. Now I get the two URIs, the first one for the first disease and the second one of the second disease. Okay, you can check if you open this link. You can see something here. You can see that it's about the muscle tissue disease that we were looking for. Okay. The same thing we can do for the Kevin. Sorry. Wrong keepers. Okay. One more. So we can do, so here we have three. So caffeine, purine alkaloid, and trimethylxanthine. And now if I have the script to get the URI, so carry with the level, and now hopefully we will get these three URIs that describe, that represent the compounds with these levels, okay? Okay, so let me see if there are any questions. No. Okay. If you have any question, please don't feel free, comfortable to ask everything you need to know. Okay. So this is the getting the URIs of a given level. So, but sometimes we have to do the opposite. Okay, we want the labels of a given URI. Okay, we have the concept that we are looking for, and now we are trying to get the labels, the names that describe that URI. And for doing that, we can also apply a CSPAN query. I'll just go here. Sorry. So this is the same query, that's the type of query that we have here. I'll just expand here. Okay. So I'll just run it. So what we are doing, we are looking for a class. Okay, we just want a class whose local name about, so the property about of class, so the property about of class is a URI. Okay, so I want the classes that have as identifier this URI, and then I will get the elements that are behind this element that I have the name label, okay, the labels of this class, okay, and then I have the text to have the contents of that label, and then I get the name malignant permeates, the label for that class, okay. We can do the same for chemical compounds. So let us search for caffeine, but in this case using the URL. So see that I'm using the URL 27742. Okay. Okay. And as we can see, we get the label that we were looking for. Okay, so let's do the same, but now for get labels instead of getting the URIs, getting the labels given the URIs. So doing the same thing, so I'll just create a shell script so you can do the same. You can open your text editor, copy. This is the same thing that we had before. This is the same thing. I'll just copy everything and then I'll clean it. Okay. And then here we have some different things. I will explain what they mean. Okay. Be careful with this character. You really need to have the right character here. Okay. So what we are doing here is the same thing. So our file is the argument that we receive. Xargs is to be applied to multiple URIs, and the URIs go here. Okay, so this is the variable of Xargs. I'm saying each line is replaced by this bracket. So I want to replace the brackets in my Xml linked XPath query by the URIs that are given by in the input, in the standard input. Then everything is the same. Then I just do some things here. So I just split the elements of that I receive as input by a new line, and then I just filter I just get rid of all the lines that have label and that have this empty lines. This is an empty line because we are doing a graph that is saying, okay, I want a line that starts with this, here and ends here and has nothing in between, so it's an empty line. And it gets rid because we are using the option V, that it's the opposite of matching. It gets all the lines that are not matching. Okay. So let me just save it. And so now if we don't forget to change the mode to be to execute the file, and then just let us try with the standard URLs that we have. And as you can see, if I give the URI for that class that describes malignant hyperthermia, I get the label malignant hyperthermia. Okay. I can do the same for the cavi. So, and get levels, and then cavi owl, and then I get caffeine as a result, because it's the label of this URI. So now I have the inverse script that I did previously. Okay, so what I can do now to see if this is everything is working is also do the same thing that I did before with the get URIs that is using multiple lines, also using multiple, in this case, multiple URIs. So just let me copy and paste here. So this is just for you to know that these two URIs is what I'm giving as input. And sorry. And now I'm just calling get labels with the ID. Okay. And as you can see, I got the labels for these two diseases. Okay. I can do the same for cavi. So let me just copy here. And just for you to see what I'm printing. Okay, so you can see that I'm giving 3 different URIs, and that if I want to know the names, the labels they have, I just call with the script that I made. Okay, so with this very simple script, we can deal with this first problem that we have in ontologies, is how to get the URI and the names directly from the OWL file. Okay, because they are the inverse function, that so one gets the URIs from a label and the other the labels from a URI. To test them, we can try to figure out applying them both to see if we reach the same result. So, for instance, in this case, I just apply malignant hyperthermia and muscle disease. Just let me show you. So these two diseases. Then I apply get URI from this ontology, and then I get the labels. Okay, from the same ontology. And what it does, okay, it uses malignant and muscle disease to get the URI, and then gets the labels from those URIs, so we reach the same result. Okay, everything is working fine. Okay, otherwise, if we had a difference here, something was not working. The same thing we can do for K. Okay, just let me show here. Sorry. Okay, so for caffeine, bruna, alkaloids, we will get also the same names that I'm giving. Okay, this is just for test. be aware that with the Cabby, this takes a little longer because it's a very large file. Okay, yes, really to look for all. Okay, let's see that. Okay, so we already did this. Okay, we can do the same for testing, starting with the URL. So let's start. This is the same thing. I will just copy and paste for you to see that everything is working. So the same thing. So here and novel. So we are now applying first the labels, applying the labels, and then trying to get the URL. So we start, sorry, no, missing the backslash here. So we reach the same result as expected from the same as beekeeper as input. And let's try for the compounds. The compounds seem also should also work the same way. So let me just copy here. Okay, this just takes a little longer, but we expect to have the same URLs that we give as input. Okay, there is a question here. Is it possible to get all the matching URIs given a partial level search as hypertermia? Yes, yes, it's possible, but that you have to make regular expressions, because in here, since we are using Shishpaf, we are just using the name of the classes. So we are like using SQL. We are just trying to find which part of the hierarchy is there. So the easiest way, if you don't want to go too much in detail, if you want to go and find all the diseases that have hypertermia in the name, we can just let me be more specific. So we found for caffeine and here. So you remember that in the beginning, we just made a graph trying to figure out which malignant hypertermia is in there. One thing you can say, okay, let me see if there is something here that is about hypertermia. Okay, so we have malignant hypertermia, and we have another thing, but it's not a label, and there is a exact synonym. This case here is anesthesia related hypertermia. Okay, so now you can search for this term, for instance, and use the same scripts. For instance, let us try. No, we cannot now because it's as exact synonym. Let me try another. We will get in a few minutes. Let me try other option without using regular expressions. Let's try this word. No, there is nothing there like hypertermia. No. Okay, this is a good example for a few minutes, because nowadays, currently we are not using synonyms. We are just using the labels. But the next slides, we will try to use the exact synonyms, and we can then try to get the URI for this type of hypertermia. Okay, so remember, if I don't talk about this. Okay, so synonyms. So it's really the next one. So we were looking for just for the label. Okay, we were looking just for these cases where we have as the label of that class. But the classes, like I said, the concepts have different names. Okay, there is an ambiguity on how we mention those diseases on the text. So we have synonyms also described in this ontology. And the way to do it is trying to find the element that is as exact synonym. And there you find the labels that can also be used. So, and we can do this by doing the same kind of queries that we had before. So this is the same thing. So I'm just copying because this is exactly the same thing we did before, getting the class, then getting the about. So both this URI, and then trying to figure out which synonyms it has. Okay. So the only difference here was that I was looking for this class that has this URI, but then instead of looking for labels, I just looked for as exact synonym. And as you can see, the same concept has two different terms. And anesthesia-related hyperthermia, that was the case that I was looking before for the question, is also as found as an exact synonym. So it means the same thing. It means the same concept. Okay. So here is another term. Okay. So if we want our scripts, our get labels to get not only just the official names, but also the synonyms, we have to change a little bit the script. Okay. So what we can do here, just let me get, here is the same thing for the, just copy to get the hard one. So I'll just clean it. So now if I want to get not just the labels, but the labels and the exact synonyms, I just add an or here. Okay. In XPath queries, we can have between brackets, we can have the or. That means, okay, it can be this name or this name. So in this sense, we get not only the exact synonyms, but also the label that we were already using. So we just need to change this on the script. So let me open the script. So get labels. Get labels here. One thing you can do is, if you don't want to destroy the previous script, you can just comment every previous command, so it's in there if you want to check it out afterwards, and just copy everything from scratch. But the only thing we are changing is the shishpad query. Okay, so the only thing I can copy everything and print it, copy words. Okay, so it's here, and then here, and then, okay, and here. This is all the same thing, but now I have to grab not only for label, but also for exact synonym as related synonym. That is another option also for finding alternative labels for a given concept. So I just save it. This is the same thing with a new query. I just apply the same thing before. I have it here, sorry. So this is the same thing we did before, but now with the get labels, now with the modification that now we get not only the official name, but also the exact synonym. So as you can see, we get anesthesia-related hyperthermia, malignant hyperexia to anesthesia, and malignant hyperthermia. Okay. No questions. Okay, so now we get the. Just let me see. Okay. Okay. So this is, we get all levels. So now let us get the URI of these synonyms and let us try here. So we get now, let us try to get the labels. Just let me clean. So get labels. This is the same thing we did before. So what I'm doing here, trying to get the labels for the malignant hyperthermia, URI, and then apply the get URI. Trying to figure out if it's still working the same way as before. So this is applying the same function that is the inverse function. So the result should be the same. But what happens is we have these problems here. It says, okay, syspap set is empty. Something is not fully working. What didn't work? So if I just clean the get URI, what happens is that it's not finding the URI for this exact synonyms, okay? Because in our script, we just try to figure out the labels, the URIs for the label and not for the exact synonym. So we have to modify also the get URI the same one. Of course, one thing in shell script that you can do, it's always to ignore these warnings because they are warnings. You can send the standard error to dev null, what means that every error, every warning goes to null. It goes away and it's not shown in the screen. But what we really should do is to clean the file get URI. So I'll just comment the previous version that we now have to update to also work with exact synonyms. So the only difference here, you can see that here we have the label, but now we have the exact synonym as related synonym and label. So we have to use everything, okay? The rest is the same as before. Here we have TR. Just let me okay. Everything is okay. So everything is the same. And now if we execute the same thing as before here, okay, we will get not the warnings, but the URIs for every term that was found. So, and they are all the same because they are synonyms of the same concept. Okay, so it's working fine. Okay. If you want to avoid repetitions, in this case, for instance, in this case, you have the same URL because they are for exact synonyms. You can just apply a sort unique. So the U is for unique, and it sorts the results and also gets rid of the same lines. Okay. Any question? No. Okay. Three. Okay. So I believe we have more 15 minutes before the coffee break. Okay, before the break. Okay, no questions. So we had now two scripts, one to get the labels, the other to get the URIs, and now we are with the right tools to start to do other things besides just getting working with the same class. Let's try working with trying to figure out the parent classes. Sometimes, for instance, in text mining, it's very useful, not just looking for the disease that we are looking for the chemical compound, but also for generic terms. Okay, some like instead of just looking for COVID, looking also for infectious disease. So we can look for generic terms, and to look for generic terms, we have the ontology that provides that information for us. So we can get the parents of that same class. How we can get those parents? So we can say now that we have the class. This is the same thing. The class, local name about with the URI that we want. So this is the malignant hyperthermia. But then we get
after having the class that we want the subclass of elements. Okay, so we want to know which concepts are have a relationship of subclass of. Okay, so the ones that are parents of this class. And then I'll just get the resource, so I get the URI. Okay, but let us try. Here, just copy and paste it. I will not apply the full. I will just go into here so you can see. Okay. So you can see, I didn't copy paste the last part, so you can see what we are looking for. So here you have the element subclass, so it's subclass of this element here, of this class here. So these are all the elements that we found here. It ends this subclass of that is a special relation. But you can see that now to find the URLs of the parents, you need to find the value that is in the resource property of that element. And this is the last part of the Xgraph query, getting the value, the property named resource. Okay, so just let me, I'm missing the backslash. And here you have. So you can see that we have the resource of each parent class of this disease. Okay. The problem now, you can say, okay, I can use string because I don't want this RDF resource here. I can just apply string and get rid of the rest. The problem is that, like I said, string only works with one out with what the first line. If we have two lines, it doesn't work. So we have to do another thing. It's something that I already did before. So we just can make something like, okay, I will do step by step so you can learn. So you can see that the output has these quotes here. So I just replace these quotes by a new line. I will just do step by step so you can see that it was split. And now to get the elements, the lines that have the URI, just make, I just want the lines that have HTTP, and then I just get the URLs. Okay. This is something that I did before in the script, but now I explain step by step. It's very easy. And now, so I just I have here the Xpath query to get the parents. So we can end this before going to the break. We can now work with our make our third script, that is get parents. Okay, so we just make a script that, in the same way as the others before, receive as an argument the ontology, and then here, let me see, here is, okay, so the same thing, Xargs, that I can give him multiple URIs, then he will look for the classes with that URI, and then you will get the subclass and then the resource, and then do that trick that I used before just to get the URI. So I'll just save it. Don't forget to change the execution mode. Okay, and just, oh, sorry, wrong copy paste. What happens when I copy everything? So, and then now we have a script get parents that, given a URI, give us the URIs of their parents. Okay, now you can see, okay, I don't know what kind of classes are these two that are parents of malignant hypertelorism. Maybe I should go to the browser and see what they are in there. But now we have a tool for doing that. We can use our own tool to know what they are about. So I can just start using my own tools. Okay, I want to know what are the parents of this disease, and then I get the labels applied to these URIs, and I see that I have these two diseases, these two names that are generic concepts of malignant hypertelorism. Okay. The same happens with caffeine. Okay, I will just do the same with caffeine. Okay. And we will get the also the names. It's in here. So the names of the parents of caffeine. Okay. The same thing. Let me see the hours. Same question. No, I believe we can do the related also. So one thing we can do also is get not only the classes that are parents, but also the related classes. And the only thing I need to change is the way I look. So I will do this for the caffeine. So all of this first part is always the same. I just want the class that is cav, that is from caffeine to caffeine. Then I want the subclass, and then just let me show you here. Okay, sorry, the rest of it here. Caffeine. Right. So I'll just try to show you what we find when we get subclasses. So all of these are things that can be related to caffeine. So they are, in a sense, inside the element subclass of, but they have a restriction saying, okay, this is not clearly apparent. It's a special kind of relation, and like we know it's the as role. So to get this information, you can see that we need to know here that if it is not a direct parent, it has this element, some values from it here. Okay, some values from give it's the element where the URI of the related classes are. So that's the reason why we now add this part and then get the resource that is where the link is. Okay. Hope I didn't make any mistake. Okay. Okay. Okay, and then you have all the links, all the resources that was in here. So I'm just getting this part, so on and so forth. So all the related classes, I can apply that trick just to get the URL. Just let me apply here. Just one part. And you can see that now I have the URLs. And of course, I don't know anything about all of these classes. One thing I can do is get the labels of this of this URL. So I just can get now apply get labels from Gary, and it will take some time, but I'll get all the information from there. Okay, and this should take a while, but probably you will get all the names that are identifying these URLs. Any question? No, probably everyone's looking for. Okay, so while we are waiting for getting these results, this is just to get the direct parents. But in ontologies, one thing we want is also to find the all parents that it has, not just the direct parents, but these grandfathers, so on and so forth, until the root term of the ontology. And this we call ancestors. But for doing that, we need a way to get the parents, and from the parents get their parents, and from their parents, and so on and so forth. So like recursive script that you will get. So these are the names of all related classes to get. And of course, we want to avoid cyclic relations. Okay, so we will talk about the ancestors after the break. And after the break and after the ancestors, we will start by applying our ontology to find things on the corpus, on a text file that was retrieved with the abstracts related with Kef. Okay, so just let me know if you have any questions. So we have half an hour or it's half an hour. So in half an hour, we will get the second part of this. Just trying to check it out if there is an okay. So if there is no further questions, I will be here for 2 minutes, okay, until 15. So if you have any question, please let me know. If don't, see you in a few moments. Okay. See you. Okay, I believe we can start the second part. So I'm sharing again the same screen, and the last thing we did was to get all the labels of the related classes to Kefin. So the idea is now to go and fetch all the ancestors. So not only the direct parents, but also the ancestors that goes from the class to the root of the ontology. Okay, so one of the first things we can do, since we have the get parents, we can apply the get parents twice. Okay, if we apply the get parents twice, we just get the grandparents. So we can try here. Okay, so you can see that we get not only the first parents, but the second parent. The first parents is just taking this one, so it's applying to these ones. These are the parents of these two parents. Okay, so we are getting the grandparents of malignant hypertrophy. Okay, of course, we can get the levels of them just to know what they are. So I just apply to the grandparents. Sorry. This is missing the ontology. So it's here. Okay. Then just copy and paste. Get levels. Okay. I was missing the .sh. Okay. So we get the autosomal genetic disease and the muscular disease that are both the parents of malignant hypertrophy. Just one thing that I fixed in the break, because the get all labels, I don't know if you saw the get labels was also showing empty lines. It was the character here. The beginning of the expression has to be really this symbol, and it was replaced by another one when we copy and paste, so don't forget. Okay, so since to get we get the grandparents, the ancestors, is we go each step until we reach the root. Okay, so we have to go until we don't have a parent. It's the root term that doesn't have a parent. For instance, the disease, the term disease, that is the root term of the ontology. If we get the parents, the result is saying, okay, the Shishpav set is empty, so there is no result for getting the parents of the root term of the ontology. The same thing happens for the root term of the Kebi ontology. So if we do the get parents here, it just takes a while because it's the large file, but you can see the same problem here, that we have Shishpav set is empty because it's the root term. Okay, so how can we do now this script that gets all the ancestors? We can simply apply recursion. Okay, I will not explain everything in detail about recursion. It's not a class about programming, but you will see that you will get the main idea of how to build a script that calls itself. So let me just create the same way we can create a script, mx get ancestors. We just copy everything here. I'll go and clean it. So you can see that you have the OWL file. That is the same thing we had before, it's the argument. Then we get this thing here that is the classes. And the classes are stored as a variable, are the ones that are given as standard input. Okay, so when we have cat and this symbol here, the minus, says that everything that goes in standard input to the script, so the file that is before giving to the script goes into this variable that is classes. So what we do is, if classes are empty, it means that we reach the root term. So there were no more parents to find were no more classes to find their parents. So this script closes when we have these classes given as input as empty. So if we have no classes, there is no parents to find. So this is the base recursion for the script. So then we do the step, if there are classes to find the parents, we find the parents. Okay, so we just echo the classes, apply the get parents for the same OWL file, just remove the repetitions, and then we print the parents. And those are the parents that we found. But of course, the parents are, we are in the ancestor script, so we need to print not only the parents, but also the ancestors of those parents. So we print first the parents, and then we get the ancestors. So we call it again the same script, but now with the parents as an argument with standard input. So this will go in the next invocation of the script into this variable and go around until it reaches an empty list. Okay, so no questions here. So I'll just save it. Hope it didn't make here. Okay, save it. And now just say that the ancestors can be executed. And now just try now to get all the ancestors of malignant hyperthermia. As you see, he's now printing the first parent, the second parent, the third parent until he reaches the last term, so the root term, that there is no more parents to find. Okay. So it's very simple. Just the idea is that, okay, we apply get parents until we don't have more classes to apply the parents. So you can see that to get rid of, we always, when we get the root term, we always try to apply that to the get parents, and we get the shishpath set is empty because there is no parents for the root term. Okay, one way to deal with that is always to apply this dev null. So if we say, okay, it goes to dev null, we don't get this error. To know the name, and also to know the name of the parent, so we can add, say, okay, we don't care about the shishpath empty, and we want not the URIs, but the labels of those URIs. So we want to know the names of the diseases that are ancestors of malignant hyperthermia. And then we get all. So you can see that the root term is disease, okay, the most generic one. So and here is all the generic cases. So it's a muscular disease. We know that is a monogenic disease and is a genetic disease, and so on and so forth. Okay. We can also do the same for caffeine. Since this is a recursive script, this is not quick. This is a very large file, but I will just put it here and it will work after some code sort from copy paste. Here, IDSync. Get ancestors, get, okay, and get labels, okay. No, I just copied 2 times, sorry. Get URI, and just clean the screen. Let me see if it is right side view. So I have to check copy again because I believe I copied also the enter and it's missing. Yeah, so just copy everything from scratch is the other solution. Okay, so this will take some time because it's applying caffeine has a lot of ancestors like we saw before, and is applying the get parents every time he finds new parents. So it will take a little while. So we will see the end result will be like this. So all of these are parents, so generic terms for caffeine. So for instance, if you are building an information retrieval system that if someone searches for caffeine and you want to also show other documents that don't have caffeine, but they are related to caffeine, probably you could also search for these terms here because they are generic terms for caffeine. Okay. So this will still running. I will just open a new tab so we can go. So the idea now, let's go for processing text. So we have the tools necessary to do the basics in trying to figure out these entities on text. So we can process now the whole file. We can get the URIs, we can get the labels, and we can get the parents, the synonyms. So we have everything ready to start to to get something from the text. And one of the things that we need to find in text is which kind of labels we want to find in text. So creating a lexicon with all the mentions that we want to find on that text. And for doing that, it's very simple now because we have the scripts. So we just say, okay, I want the URI of malignant hyperthermia, and from malignant hyperthermia, I just want all the labels that it has. Okay, I will just bring before, sorry, missing the dots. So I will just get, these are the terms, like I said before, that are the synonyms. So this lexicon, if I now redirect this output to the file, I just get, as you can see here, I just get in the file the same elements there. So this can be, if I'm looking for documents that are related to malignant hyperthermia, I should check for those mentions on text, okay? But of course, if I made a script trying to figure out all the generic terms for that disease, I can also get all the ancestors and add it to the lexicon. How I can do this? By doing exactly the same, but instead of getting just the labels, I can get the ancestors. So I can get here the ancestors and add to the file. You can see it is, it's not only one redirection operator, it's two. This means that I'm not creating a new file, but adding to the file that I already have there. So it will add to the file that I created before. So it will create with all ancestors on malignant hyperthermia. Let me see, this is still running. So this will now apply the get ancestors to malignant hyperthermia, and we can check which kind of labels we now have there. So this is our lexicon. If we want to find documents about malignant hyperthermia, we can now search for all these labels here. Okay. Of course, some of them are very generic, like disease, and you can make a cutoff. Okay, I just want to go until this level of hierarchy. But here we will do with everything. Okay. So I just did what I said here, just to find. We can do the same thing for caffeine. So if we want all the labels for caffeine, sorry, just copy again. The labels for caffeine. So this is all the labels that we found before, and then I can create a lexicon with it. Okay, it's still waiting for the other one. So you can see that it's only caffeine. We just can add this to the file. Okay, and we have caffeine there. Okay, we are working with the same file in two directions. So that's the reason why this is small. So here we just have caffeine, and after we get this, we will run the same command with the get ancestors. Okay. So one thing we can do, we can merge both things. So we can have a large lexicon where we can have all the dimensions for caffeine and all the mentions for the disease. But for our example here, since we are still waiting for the ancestors, we will just use the disease. Okay. So now to try to do let me see if there is any question. No. Okay. So if we now want to do some text mining, so one thing we can do is to apply this, to try to find the elements of this lexicon in a corpus. And for doing that, we need a corpus. I'm just using the one that is used also in the book, that is retrieved in the first chapters of the book, that is text related with caffeine. Okay, so this is the link that is in the book. We're just getting all the files in there, and then we will just get the sentences. So a file that is caffeine sentences. So this is the number of the caffeine entry with all the sentences there. And then to recognize if there is something in there, we just need, there is an echo here in the LaTeX file, but to find the comment in there, the mentions of our lexicon in the cabbie sentence, we just need to do this. I will just use just only the diseases, like I said before, so I'll just add it here. And now you can see that we are now starting to do some kind of text mining. So we are finding the sentence that mention malignant hyperthermia. Not only malignant hyperthermia, but the ones that also reference other terms. Okay, so what other terms? The ones that are parents and grandparents of malignant hyperthermia. So you can see there are a lot of sentences and a lot of results for malignant hyperthermia in this corpus. Okay, so this graph here is just trying to figure out, it's a graph with multiple options. So the W means that we are trying to match the whole word. So each term has to be found in the corpus as a word. E, the I is to ignore case. The F, the uppercase F, is to say that, okay, I have in there terms that are really text to find. Don't try to figure out special characters in there, like regular expressions. And then the file where I have all the labels to find in the corpus, okay, in this file. So this is the line, the matches, the patterns that I want to find in this second text file. Okay. Is there any question? No. Okay. So let's go forward. Let me see. Sorry. Okay, so it's already stopped. As you can see, there are multiple paths until the root. So these are all the ancestors of caffeine. So let's add all of them to the to our file. I just can apply here. Let me go here. It was this one that I didn't make. So just adding all the ancestors to our lexicon file. So just copy. It will run again. I could copy it to here, but let it run. Okay. So it will run again. Okay. So to see, so these were the grep function that option that we use to find the mentions of malignant hyperthermia, and these are some examples of the molecular ancestor of caffeine that is matched here. If we had the caffeine in the lexicon, how can we see which ancestors are being matched? The ones that are not the direct label, but the ancestors. One thing we can do is apply again the same grep, but we give now the option O. That means that instead of the sentence, it gives me the labels that were matched in the corpus, and then I just make a sort. And we don't have this lexicon yet, so say what just the diseases. And you can see that we find disease and malignant hyperthermia. These are just the two terms that we find in there. when we have this lexicon from Kevin, then we will find also Kevin and molecule. There are two accesses in there. This is very specific corpus. That's the reason why we don't find any other terms. So we can apply afterwards. Okay. Okay, so one of the things that we are doing here is a very specific retrieval. So we want all the sentences, all the abstracts in a way that mention malignant hyperthermia. But if we want a generic lexicon, so I just want to find all the diseases that are in there, or all the diseases that are in abstracts, we can also do that. Because we have ontology, we can get all the labels from ontology without any problem. So one way to do it is applying our command XML links that we already know. So just copy and paste it here. And here. Okay. And so you can see that since I'm not giving the restriction to be any URI, I just want the labels exact synonym and related synonym, I get all the names of that are possible to find in the disease. So let's make a script to get all of that. So we can make a get all label script that gets all these labels that are in here inside these elements. So let's make it. Once again, if you have any questions, please let me know. So I'll just clean these things. Don't forget to replace this character here. Okay. So this is the same we had before. The only difference is that we don't try to figure out which URI. We don't receive URI. We just keep every class from every exact synonym, every label, every related synonym for every class. Okay, so we just save it. And now don't forget to get change the file to executable, and then we can execute, and you see we have all the diseases that we have in ontology. Okay, all the mentions that we have in there. Okay, so we can create a very simple lexicon with all the diseases, human diseases that are represented in the human disease ontology. Any question? No. Good. So we cannot use this instead of just reading this on the screen. I just can create just a disease here. Okay. Lexicon. So all of these are all of the diseases are in here. I can use the word count lines using the lines option to see how many lines we have. So we have more than 34,000 diseases in our lexicon. Okay, so labels of diseases. So let's try to use now this lexicon to try to figure out matches that we have on our portal. So we just can just go there and supply a grep. But we have a problem. Okay, what is the problem? There are some elements in the diseases that use brackets. Okay, and brackets are special characters for grep, and it tries to treat it as a special character in regular expressions. but here are just the name of the label. So one way to fix it is just replace the expression for, instead of regular expression, using the -f that we had. And here you have the number of the line and where the malignancy, the disease was found. Now you can see that we have different diseases like myopathy and central core diseases. So there are many different diseases now that are found in the text. But still there are some problems by just using this trick of saying, oh, everything is text and we just want to find the exact match for each term in the text. What is the problem? Is that some of them have these parents, and we will not find most probably a mention of these diseases with these brackets. Okay, normally they are just using the name. The brackets is something that the human was doing there, and when the curator of the ontology was defining the disease, just added these brackets. Okay, so it's getting problems, just a problem for text. So we have also the problems like separation characters, like here we have columns, commas, so everything can be a problem to find these, because these again will not be present in the text. Normally we don't get these names mentioned in the text like this. And also comma also being part of the term, like this one. Sometimes we cannot just remove the comma as it is. We have other problems like having these HTML characters in there. But there are alternatives normally there, so this is not really a very problematic case. Okay, just to see how many problematic cases we have, we can just make a graph. We just want to copy everything else, just slide. So -c is saying, okay, I want to count how many brackets, beginning of brackets we have in diseases. So you see, you have more than 1,000 labels have this kind of brackets, commas. So you still have more, and these are not so much, and the other is also not so much. But all of them are problems that we need to solve. And what kind of problems we have with this structure in the labels? For instance, if we make a graph, just trying to find, don't forget to replace this character here. We will see that we have in the diseases starting with ATR, we have all these labels in our lexicon. All of them start with ATR, but none of them are just ATR. So if we have a text like this one, where I have the ATR syndrome, so on and so forth, and I want to grab if there is ATR in there, I just need to have ATR as a single label in the file. If we apply to the diseases, we will not get the match. Like, for instance, if we just put in here diseases, the ATF will not be matched because it's not in there. Okay, it's syndrome, it's alpha thalassemia, but not ATR. Okay, because ATR it's not there alone. Okay, so one way trying to fix this problem is removing all the brackets. Okay, so just like remove all the brackets and parentheses. So I just put the comments that replaces a character by another. In this case, I use the option -d that deletes these characters. Okay, so sorry. So I just, by doing this, then I try to figure out if I just found the term that I had before with the sorter, and you will see that there is no brackets now. So it gets rid of all the brackets in there. So now we can also remove the extra term. So one thing to solve is to try to get rid of the extra terms that we have after the comma, like this one. So we don't need this. We just want to find in the text just the first part of the label. And one way to do it is just by making applying a set operation. So I just apply set here where I replace. So this is replacing after. So I first find the character that is separating the label, and then I find the space, and then I clean every character until the end. Okay, and I just replace it by nothing, and so we get rid of those characters. To see, for instance, now for what happened to ATF, the form that we had a little while ago. Now we can see that we get rid of the second part of the label, and now we have ATF in our lexicon. Okay, so another thing is also sometimes we have extra spaces on the labels, and if we have spaces on the labels, then we will find have to find the spaces on the text, and we don't want it because we just want to find the labels. And so one way to do it is also replacing with a set. We just replace it just here. So we just the last two is just replacing the starting and the end of the label that has spaces by nothing. Just remove it. Okay, and we have it again. Okay, so all of these steps here, we can join this to our get all labels. So instead of just getting all the labels without any pre-processing, now we have this very simple pre-processing just to get the best that we can without any fancy things. The labels all cleaned up. So let's open the get all labels. And here you can see that everything goes the same. Oh, sorry, this is the get all labels. Okay, XML link is the same, TF is the same, grep is the same, and now here we will just replace this by this and apply the set and add the sort. So it is not in the end. Okay, so and now we apply the get all labels to our diseases, but now we have that kind of preprocessing. Okay, so now we reduce the diseases. It's not so many as before. Why? Because by cleaning all those characters and parts of the labels, some of them became the same, and they were removed since we are doing the sort minus U that just keeps the unique labels. Okay, so trying to do some recognition of the diseases now. So we can now try to figure out using our diseases lexicon, which can be found in the sentence. And now we can see that all of these diseases are found in there. I just use the -O option that instead of the sentence where it was matched, just give me the matches and the number where it was found. So in this line number 1107, central core disease was found. Okay, so to see how many were really found, we can just make a sort, remove the number, because and this gives us all the diseases that can be found in the file. Okay, so all of these diseases were described in our corpus. Okay, to see how many, you just can have the word count, and then we see that we have 47 diseases in there. Okay. Just let me see here. Okay, I have here 66, but I really we didn't check the same term. Sorry, I have it here. So this was 47 diseases that we have, and now going into this slide, the difference that I made was having the ignore case. So I just added this option here. I will just have it here. And what happens is I get much more matches. What happened was, let me show what happens here. Just checking, is that you will not only find malignant hyperthermia as the label is written, but all the other options with different uppercase, lowercase alternatives. So for instance, malignant hyperthermia can be found everything in uppercase, just the first letter in uppercase, or the first and the second word with the first letter in uppercase. So one way to see which ones were new to be recognized, we can do the same thing that we did before with the ignore case and add this to a file. So this is recognize ignore case. So this will list these matches that we have here, and now we do the same, but recognize without the ignore case. So we remove the I from the match, and then we just try to figure out what they are different. So I'm now making a trick that is trying to figure out which of the recognized are in the recognized ignore case, and I remove the ones that aren't. So in that sense, I get all the ones that are in the recognized and not were found by, that would found with ignore case, but not with the recognized. And you can see that we have all this difference here. So we have all and all, that is a disease, malignant hyperthermia, like I said before. Okay, so all of them, all of these diseases were found by using the ignore case. Otherwise, we were missing these diseases because they were not found as labels. Okay. So the one of the cases was this disease here, this inesia, and one way to check it is if you go to your file, you can see that the only option that you have is with the uppercase T. So it means that you will not find unless you do the ignore case. Okay. Then you can also check that index discrete appears in lowercase. So one can ask, okay, so we don't want to miss anything, so we just use ignore case. The problem of using ignore case is that then we open the door to also to multiple false positives. Because, for instance, acronyms that have the uppercase, all the characters are in uppercase. If we apply ignore case matches, then we get words that are not the acronyms. For instance, one example is the CAN. CAN is a disease, an acronym of a disease. And let's see if it is, I'm just checking if it is found in the corpus. So I'm just seeing here that in line, there are 18 matches for CAN in the file. So you can see the one. So, and you can see that all the matches are CAN or cancer, but cancer because we are not using the word match, okay? And here you just can have the word match that it can. Okay. So we have this all mismatches in here. So it's always, this is just to say that it's not always a good idea to use ignore case because we can have a lot of these results that were not what we were expecting. Okay. Sorry, I just made here to see just the matches. This one, sorry, I was missing here. Expression, no, what I'm missing. It's okay. I have the. Sorry, because I don't need the number. I don't need the number to see what type of matches were found. I just remove the n number and I just have all the matches that I have. Okay, starting and ending with can to avoid having the cancel. Okay. Any question before going into entity linking? Okay. So that is one thing that we know. Okay, it's to find the mentions of those diseases on the text. But now one of the things that we did is finding those mentions. Then we also want to find which URI is representing that disease that was found in the text. So we are just trying to figure out many diseases, to match many diseases in the corpus. Let's figure out which of those matches can be linked to an ontology entry. So we'll just go here. And what I'm doing is just getting all the labels for this acronym. And you can see that we have AD2, Alzheimer's disease 2, so it's Alzheimer's disease and there's different labels. But the problem is that we just change some of these characters. So for instance, here, if you try to figure out, for instance, ATF, to get the URI in the disease ontology of ATF, it's not there. But it is in our disease file. So if you grab ATF in our diseases, so sorry, just to get the all match, it is in the disease is there. We are trying to find ATF, but we cannot find the URI of ATF. Why? Because it was a modified label. This is one of the labels that we modified during those steps. And then we have a problem. One solution is to keep track of the original label so we can get the right link. Otherwise, we will not get the right link because this is not the solution that we had before. Okay, and then we have here the most interesting problem, that is ambiguity. Sometimes the same label, the same acronym can mean two things. So if you just try to figure out what is the URI of this acronym, of this disease, and we assume that this is a disease, it gives us two URIs, two different URIs. What this means is that probably both classes have KOS as a label. So they represent namely two different diseases, so Kaufman oculocerebrofacial syndrome and Kagami-Ogata syndrome, okay? And both these two diseases can be referred as KOS. So we can also try to figure out what they mean. So just making echo from the URL. This is in the problem to copy. I'll just copy from here. Right. Echo. And then okay, you can see that for this class we have for the Kaufman disease syndrome, we have cause as a label, as a synonym. And for the other one, I'll just put the number because it's easier. So it's 111712. Okay. And we get also as a synonym to the Kagami-Ogata syndrome. Okay. So we have ambiguity here. So if we have a text like KOS is a syndromic intellectual disability, and we want to find, we want to perform entity linking, so we want not only to find that KOS is a disease, but it is also what kind of disease it is, so linked to the class, the correct class. We need to do some kind of disambiguation. So let us just check how this works. So if I just try to figure out all of the diseases, just trying to match all the diseases in the text, you can see, okay, I found that KOS is a disease and syndromic intellectual disability is also a disease. So there are two diseases. What is the problem is that KOS can mean two diseases and I have to select just one of them. So if we want to find the URI, just so I can demonstrate what I told you. So you can see that we have two URIs for KOS and just one for syndromic intellectual disability. So one simple way to disambiguate is to use semantic similarity. So it's the thing that I told you in the beginning about context. So every abstract, every sentence has a context. And this sentence here is as a context, okay? Because I just mentioned KOS, but then I give a clue about what is KOS. In this case, it's a very direct one, but sometimes it appears in the text. Similar terms are in there. So when I have a question, which class represents that mention, and we have ambiguation, a good solution is trying to figure out of those two solutions, what is the one that is more similar to the other ones. And this can be done by using semantic similarity. So we can just calculate the semantic similarity by using a tool. There are many tools to calculate semantic similarity, but in a way, to see how close they are in the graph to each other. So if we go to this website and just paste it here, this identifier of Kaufman oculocerebrofacial syndrome, so this first option that we have here, and we calculate the semantic similarity with the syndromic intellectual disability, we get these values. Okay, we get that there are some similarity between them. So I will not explain in detail these measures, but there are different measures. These last two are normalized between 0 and 1, and you can see that we have here at least greater than 0 similarities. But if we do the same, but now for the other option, for this option here that represents the other option for QoS, that is Kogami-Ogata, this one here, and calculate the semantic similarity with the similarity with syndromic intellectual disability, we will get a 0 similarity. Okay, almost 0 in all the metrics. That means that the Kaufman syndrome, it's much closer to another term that was found in the text, to this disease here. So this solves our problem. We can figure out which are the most similar option and then select that as the right link to that is described, the right disease that is described in the text. We can do this, of course, also in command line. So this is what I said. One way is to use the Shin. It can be installed within GitHub, but one very easy thing to do is just get this is Python. Okay, there are packages just for this, but one thing very easy to do is just download the files, the Python files. There, you just need two Python files, and then you need the database, because it uses the database that was created with the disease ontology. And so I just downloading the database, then I just unzip the database, okay. So the only thing you need is to install Python or Python 3 if you don't have it, and SQLite, because it's a database in the SQLite, but normally it's very easy to install. And then to calculate the similarity, just run the scripts. So this is between the first option, the second option. So you can see the results that we saw in the web are here also, and you can see that this is much similar. So we should select this disease as the right link to the mention of QoS in the sentence. Okay. Any question here? Just seeing, probably I was too quick here. I don't know if you got the thing, the installation of the machine. Is not the installation, it's just retrieving the files and writing the results. Okay, it's something that you should get. Of course, you can go also to the webpage. Let us try go to the webpage, and it's the same thing. So if you go here to the webpage, copy, just open the webpage, add in the link, and you can check that the results are the same. You just copy the various options here, and you see that the result, and you can copy. Yeah. Okay, you can do the same with different totals. Okay, this is a tool, but the questions that we had before, if this works with the generic terms, but we have WordNet here. You can calculate similarity in WordNet, in Mesh, Radlex, in human phenotypes, in ontology, so on and so forth. Okay. Okay. So we are almost there. So one thing, sometimes we have a problem is then when we have a large number of words that we want to find in the corpus, then it gets the performance is not so great because it's a very large corpus and it's trying to find each line in the lexicon, trying to figure out if it is in our corpus or not. And like I said before, that we have a tool, for instance, that is all built in shell script that is very efficient in dealing with that, and it's very easy to install. It's also a shell script. So what we will do now is just trying to use this tool with our lexicon, with the disease ontology, and trying to figure out what it can find in that corpus. And the two things that we do, it does the recognition with some more advanced preprocessing and also the entity link. So we can just clone the tool here. So it will get everything from GitHub. It just takes some moments from the network. Okay, the megabytes are about the data set. So, and then we just copy our file, our diseases, our file to the data folder of the tool. So it just creates the lexicon directly from an ontology, from OWL. Then we enter in the folder of the tool. Okay, we are just in the tool. And then we need to do some preprocessing. So we just go into the folder of the tool and just produce the data files from and you can see that it's very quick. And what it does, it divides the lexicon in multiple files, one with the diseases that have only one name, the others that have two names, the other have two words, have three words and more than 3 words. So now we can, this is what it has shown. We can now remove, we are now able to remove the OWL file because we just need the lexicons that he created. We can check what is in there by just making tail and all the files that are in there. So you can see that, like I said, this is the words that contains the diseases with multiple words. Then the ones that have just 2 words associated with 1 word and the whole lexicon. And here, the most important here is that we have the relation between the terms and the identifier. So that's the way this tool can perform the entity linking. It doesn't lose the links between the matches. Okay. So to execute is very simple. So we just get our file and remove all the quotes because quotes can be a problem to invoke this from the terminal. So then I just So for each line in the corpus, it will apply the script get entities. Okay, so for each sentence given from the sentence corpus, it will apply get entities and using the DOID files, so the disease. So if we apply, you can see that he gets not only the disease, the place in the sentence where it was found, so the beginning character and the end character, and also the links for the diseases that were found. Okay, so this is a very large numbers of diseases, and just let me see, it's already stopped. Okay, this. So these are all the diseases. He's trying to match all the diseases found in the corpus. And the first number, like I said, is the start and the ending character often mentioned in the house. All of these mentions can also be redirected to a file, in this case a TSV file, to a file separated by tabs. All of these are separated by tabs, and we can open this in any spreadsheet application that we are used to work with. So, and that's the end. So this is just finished. I will just redirect this to a file, so you can see that this can be opened in a file. So in the end, all this shell script to deal with, we were able to, in a few hours, not only to get information from the ontologies, to work with parents, synonyms, so on and so forth, get the ancestors, but then use that information to do some text mining and to find those diseases on the text. And all of this was done with very simple command lines. Of course, if you want to apply more efficient tools, you have to do now the next step, the next level, going to the next level to use deep learning techniques, transform, and so on and so forth. But the idea here is for you to learn how to use these resources, the ontologies, and how very simple you can check if these resources can be helpful or not in your corpus. Okay, that's the main lesson. Mir is also available on the web, so if you want to use the tool, let me just check it here. You also have the same option as the Sheen to use on the web. So we just select the disease, for instance, diseases. This is a text, and it keeps, okay, it found influenza in the beginning, then disease, influenza, infection, disease, and then runny nose. And if you, this is the entity linking. So if you click here, you will go to the this is the runny nose. I click it here, and it goes to the disease class, the definition of runny nose, and you can see that everything is explained here. Okay, so runny nose, you can see that is a synonym for runniness. Okay, this is already finished here also, so I just can open the file in the folders. So let me. So this is what we made. Sort of the files that we get, and this is the connection. You can open in any spreadsheet. Okay, this is a tab separated value that you can then filter and work wherever you want with the file. Okay. Any questions? No. If there is no questions, I will end this tutorial. And if you have any problems in replicating the things here, you can go to the book. You can send me an email, and I'll be I'll help in any way I can. Okay. Thank you very much for listening, and hope you enjoy the conference.